Picture an average night at home. You're sitting on the couch, remote in hand, maybe with a beverage by your side. You use your remote to navigate through the menu of your favorite streaming platform to select an episode of your favorite TV show. You pause to give a command to your smart speaker to shut off the music you were playing before sitting down. As you watch the show, you recognize an actor you like, but you can't remember where from. So you grab your mobile phone and run a search in your internet browser. Satisfied with the answer, you speak into your smartwatch to set a reminder for later to watch a different show starring the same actor. All the while you are lounging with your feet up and feeling quite relaxed, never thinking about the bank of server blades in a data center far away, working tirelessly to power the cloud that brings this convenience to the palm of your hand. Our lives are increasingly dependent on the cloud, and whether we realize it or not, those data centers are growing and using an amazing amount of energy. How could microchip technology help address the growing need for data centers in a sustainable way without compromising our new standard of life? Let's go beyond the microchip and hear a story of empowering innovation to enhance the human experience. Our guests today are Ashish Maktal and Max Prasad. Ashish and Max are senior engineers at Microchip Technology, working out of the 8-bit microcontroller business unit. They join us today from our global headquarters in Chandler, Arizona. Welcome, Ashish. Max.
Hey.
Thank you for joining us on Beyond the Microchip. In the intro, we briefly talked about our increasing dependence on the cloud and the effect that data centers have on our lives. Can you tell us more about that?
Sure. With the advancement of technology and convenience, our lives are more and more dependent on cloud than they have ever been before. From the moment we wake up to the time we go to bed, many aspects of our lives are facilitated and made more convenient with the help of technology. Whether it is talking to a smart speaker or accessing information on your cell phone, communicating with friends and family over video calls, conducting business transactions online, attending meetings online, or enjoying any form of digital entertainment like this podcast. All of these and many more such services are powered by data centers. And what is a data center? If that's the question, imagine it as a gigantic, ultra organized library for computers and not for books. And this libraries doesn't just store information. It is where all your favorite apps, your websites, your personal photos, your messages, this is where they all live. Picture rows and rows of super fast computers that are neatly stacked in racks, and they're all connected with a web of cables. These computers, they work together to not just store the data, but also process the data to ensure that every time you hit like or you send a message, everything happens in the blink of an eye and it is completely seamless to the user. Data centers in general just play a very crucial role in our lives. We just don't realize it.
So the processing part I understand, but what about the storage aspect of it?
Yeah, storage is actually a big part of data centers. Think about a movie that you're watching. That movie has to be stored somewhere. It's usually stored in drives, or solid state drives that are stored in the data centers. Like Ashish mentioned, think about not small, but like a solid state drive, but lots of them, thousands and thousands of them connected to hundreds of server racks all across the building, all over the data centers. So data storage is a big part of any data center. But then accessing the data from that drive is another thing. Think about you're streaming a movie. When you're streaming a movie, there's two major components to data transfer. First component is high-speed transfer. For example, when you're watching a 4K movie, then a lot of pixels, a lot of data needs to be transferred really quick.
High resolution. Yeah.
Exactly, right? That to like 30 frames per second, 60 frames per second, it has to be real quick. So for that, typically a high bandwidth data transfer route is taken. That typically happens over PCIe, which is great. It works great for fast data transfer. But then there are other auxiliary functions that also need to be performed that don't need as much of the high bandwidth. For example, you want to stop the movie or start the movie, right? You want to, or let's say the fan speed needs to be controlled in that solid state drive. Or another example could be that you want to learn about the speed requirements of that drive. Is that what's the maximum speed that drive can read or write at? So all these are auxiliary functions. We call them sideband because it doesn't require the main band communication. It happens on the side, but it's essential to improve the overall user
It's
experience.
what's going on in the background. That's
Exactly.
not the actual movie itself. It's what's helping bring the movie to the screen.
Exactly.
Yep. And just to add to what Max said, right? These auxiliary functions, the sideband control that he mentioned, up until now, traditionally a protocol called as I2C was used to do this. I2C or I2C, as many like to call it, it's the classic GIF versus GIF of the embedded systems universe. I2C stands for inter-integrated circuit communication. At its core, it is a two-wire protocol which is used to send data and commands between two chips. And like Max mentioned earlier, it's not the actual data that's being transferred, the movie or the file that you're trying to access, but it's all these other auxiliary functions like monitoring the temperature of the drive, how full is the drive, where do you start to read, when do you stop to read. All of these are dependent on I2C. And I2C as a protocol was developed in the 1980s, early 1980s by Philips. And it has evolved since then as technology changed and improved, so did I2C along with it. But I think we have now come to a point where we needed something new, keep up with the demand, not just the current demand, but the future demand. Going back to point of our lives being more dependent on the cloud. So a group of companies got together, and it's called MIPI, spelled as MIPI. It's just an alliance of companies that focuses on developing hardware and software interfaces for connecting chips together. MIPI developed the I3C protocol or I3C. Back to the GIF versus GIF problem. Yep. We did not solve that problem. But I3C was developed to address the limitations of I2C. In general, the purpose of having I3C is to help the overall system improve its response time and consume low power. Because like Max mentioned, there are thousands and thousands of drives spread across thousands and thousands of data centers all across the world. Any small amount of power that we can save on each drive will add up eventually.
Right, because there's a lot of actions going here back and forth. We're not just talking about the content being brought to the network. There's all of these extra little functions of the server that are actually being taken care of, right?
Yep.
And the I2C protocol works, just doesn't work as well as I3C.
Yes. Today, like I said, I2C is used today, but
it has limitations.
I2C has its own limitations, and that's where I3C comes into play.
So what are the improvements over I2C?
Definitely. So, well, I3C, if you're wondering, I3C stands for improved I2C. So
okay, so there is still the letter component.
Yes, exactly.
This is the GIF versus GIF argument.
Exactly. Yes, so that there are some improvements, many improvements actually, but one of the major improvements is when it comes to speed. I2C can go up to 1 megahertz, whereas I3C can go up to 12.5 megahertz, like raw bus frequency.
At least an order of magnitude.
Yes, exactly. But it's not just the bus frequency, but you can also encode the data in such a way that the data transfer can happen at a much faster bit rate as well. It can go up to 33 megabits per second, which is much, much higher than what I2C can deliver. Well, speed improvement is one thing. The other improvement is in regards to power, what Ashish was mentioning. I2C traditionally has been used at 3.3 volts or 5 volts, so higher voltage levels. And because it also uses open drain communication, it requires more power. However, for I3C, because I3C has been designed to operate at lower voltages, like as low as 1 volt. So the specification says it can go anywhere from 1 volt to 3.6 volts. So that's the range. So it's ideally for lower voltage operation like 1 volt, 1.8 volt, which reduces the power consumption. The data transfer also happens in push-pull mode, which also reduces the power consumption. So there are a lot of power consumption benefits as well.
This is across the entire data center?
Yes.
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 Every drive that would end up using I3C will start seeing these benefits.
Right, and we're talking about drives in the thousands. And,
Yes.
and your average data center is hundreds or even thousands of square feet.
Yeah.
Mm-hmm.
Yeah.
Definitely.
That adds up over time.
That adds up over time.
Yeah. Another improvement is in regards to the layout of the board that are designed, because I2C is a 2-wire interface, but that 2-wire is just for transferring the data. But sometimes there are additional signal lines also needed for interrupts or reset or other things as well, which increases the number of lines that are used for a typical I2C communication. In I3C, there are ways to make sure that all these extra functions like interrupts, reset happen in band through those 2 wires as well. So I3C is a true 2-wire interface. You'll just need 2 wires, one for data, one for clock to do everything that you need. Unlike I2C, where you would also need other lines to do some additional functions.
Which increases complexity.
Exactly, definitely. And all of that while mentioning that I3C is backward compatible with I2C.
Okay, so you don't have to do a full I3C upgrade. You can take your time as budget and resources allow.
Yeah, definitely. Yeah. Just to add a little more to what Max said about backwards compatibility. I think that in itself is one of the key components of the industry adopting I3C. We discussed the scale of data centers. It's so large that it's almost impossible to upgrade all the systems at the same time. It's not physically and financially possible to do that. Upgrades can and probably will happen over time, and until it is critical to have the new drive plugged into there, and more so, it is just focusing on the backwards compatibility a little more. We want the new drive to be able to be plugged into an older system as well, or have an older drive being plugged into a newer system, and everything should still work, right? The change is not going to happen overnight. So we want to have a way in which the older system and the newer system, and the older drives and the newer drives can coexist. And the beauty of I3C is that since it's backwards compatible to I2C, which was the legacy protocol used until now, the transition should be seamless.
Mm-hmm. So you're suggesting that upgrades should happen in sequence, or what's the best way to do the transition from 2 to 3?
They're typically, so we see it happen in 2 ways. One is where the SSDs are updated. So usually whatever the solid state drives are being used, right, as they are being replaced with newer solid state drives, they will be supporting I3C. So, but the main server rack may not support I3C yet. So typically it would start with upgrading the solid state drives that are in the data center, and then eventually upgrading the server rack as well. Usually, like Ashish mentioned, it can also happen the other way around. It could be that the server rack is being updated, but they're still keeping the same old solid state drives until it is time to upgrade them. So it can happen in a phased manner.
And we talked about main band versus sideband communication. Can you give us some examples of how I3C is used for performing sideband communications?
Yeah, definitely. Think about when a solid state drive is plugged into a server rack. The high bandwidth communication that I mentioned earlier typically happens at a much higher voltage, like 12 volts, or it requires a 12 volt power supply to power up the main solid state drive. But before the solid state drive is powered up, what the main server rack does is that it detects that, okay, there's a new drive that has been plugged in. So instead of turning on the main power supply, it turns on an auxiliary power supply, which is at a much lower voltage, like 3.3 or 1.8 volts. So it turns on that auxiliary power supply, and it reads certain vital information. We call it vital product data from the drive that was just plugged in. Think of it like a sticky note that's attached to a drive. So it's reading some basic information like, okay, what's the size, what's the capacity, what's the maximum speed it can read, all that good stuff. And then when it detects that, okay, a legitimate drive has been added and it knows all of its functionality and features and speed requirements, then it goes ahead and turns on the main power supply. So before it turns on the main power supply, all of this communication where it is reading the vital product data, that happens over I3C.
Right. So it's not the primary function of the server. This is just the way that the server operates itself.
Yeah. Just one more example of an extension to what Max just said. Let's assume that we have a new drive that has now been plugged in and it is now activated and working. The data center admin would like to monitor several parameters of this drive. And this is just to ensure that the drive is healthy and the performance is optimal. Things like temperature of the drive. Were there any read or write errors on the drive? What's the power consumption of each of these drives? How's the endurance level of the drive? Even stuff like firmware updates of the drive can be monitored through this sideband communication that we were talking. And let's say it is observed that one of the drives in one of the server racks is overheating due to some malfunction. A command can be sent to increase the fan speed to improve the cooling of that one drive. Or if a drive is slowing down because it's being overused, it can be reported that we are seeing some errors on this drive. So you might want to replace it with a newer drive before it fails completely. So you can do some sort of preventive maintenance by monitoring these different parameters of the drives as well.
This is good for maintaining uptime in the system.
Yep.
The last thing you want is that circling thing on your Netflix movie, right?
Exactly. Everyone hates that.
So which devices apply to the applications we've been talking about today?
The device that primarily applies for this application is a PIC18 Q20 family of devices. It is a PIC18 microcontroller which has two I3C modules. And it has been designed in such a way that because it has two I3C modules, it can actually talk to the main solid-state drive controller and the server rack, the BMC, or the management controller chip on the server rack at the same time through two separate interfaces. And it also has support for something called multi-voltage I/O. What that means is that it allows for a separate power domain in the chip itself, which allows I3C to communicate as low as 1 volts. Another feature or benefit of Q20, the PIC18 Q20 device, is that it comes in a very small form factor, as small as 3 millimeter by 3 millimeter. It is a really small, tiny device that can go into small spaces, small solid-state drives, server racks, anywhere. And in addition to that, it is a low-power device. There are many server racks that have current limitations on how much current the auxiliary or sideband functions can use. Q20, being a low-power device, is easily able to meet those power requirements.
So as to not take power away from the main band?
Yeah, but I mean, the limitations are more so for the overall system. These are specs that are in place, again, by different agencies, which want to monitor how much power is consumed by each server rack. So there are limitations that are in place. And as a designer for a drive that is going to be plugged into one of these server racks, you would want to consume as little power as possible. You don't want to be operating at the limit of the spec. You want to have some leeway so that in case something goes bad or you have chances to improve your design. So you would want to be as far away from that limit as possible. And the Q20 being a low power device, it can help you do that.
Mm-hmm.
And to aid our developers who are using PIC18 Q20 device to develop applications, we have lots of tools available, development tools. Mm-hmm. The primary one is a Curiosity Nano board that's available for the PIC18 16Q20 part, which is a small little board that works great. We also have I3C APIs available for our software developers to use through MCC Melody framework, through MPLAB IDE, yes. We have lots of code examples that uses those APIs. We have tech briefs available, app notes available for people to learn about I3C and how I3C can be used in a certain application. We have all of those available. And in addition to that, we have also partnered up with a company called Binio. And Binio has has developed many things, but it also has something called an I3C protocol analyzer that works on top of a SAILI logic analyzer.
Mhm.
So actually, as a special promotion, anyone who ends up buying a PIC 18F16Q20 Curiosity Nano board, they get a free 45-day trial of the Binio I3C protocol analyzer. Yes.
Nice value.
Yes, definitely. And in addition to that, because the PIC 18 Q20 part has the target version of the I3C, Binio also makes a Supernova I3C controller that can be used alongside the PIC 18 Q20 part to complete the entire transaction.
So suppose one of our listeners has a use case for this technology. Where would they go? Where could we send them?
I mean, you can start by going to microchip.com/PIC18-Q20.
Okay.
This is where you can learn more about the microcontroller itself, and you can get access to the application notes and code examples and other collateral needed to get started with I3C. I believe we also have a link over there to the Binio stuff that Max just mentioned. And the Curiosity board that Max mentioned is probably the best way to get started with I3C. It'll help you prototype and help you design, help you get started with your design fairly quickly.
Do you have any predictions for the future of the I3C protocol and how the technology could enhance the human experience, like examples we talked about today? Where's this going? I mean, what's the... this may be a silly question, but we can assume an I4C at some point?
Maybe at some point. We don't know what that point is, but I can tell you that I3C, yes, right now it's being started to be adopted in the data center industry and data center applications. However, we do envision it to grow and expand into different sensor node applications, industrial automation, and other control applications as well.
Yeah, and like I mentioned before, it is backwards compatible with I2C. That's one of the key features. And I3C was designed to be used wherever I2C is used today and beyond, right? The developers can start upgrading to I3C without breaking any of their current systems that work on I2C. That's the key. The transition is going to be steady and seamless, I believe. A good example I can give you is the transition that we all went through from USB-A connectors to USB-C connectors. USB-C connector, Type-C connector was probably introduced in, 2014, 2015 timeframe, I guess. And we are probably 10 years into it now. And now I think we're getting to a point where we see a lot of devices switch over to the USB-C connector.
Yeah, most prominent being the iPhone.
Yes, exactly. That doesn't mean USB-A has gone away completely. It's still around, but I think if someone is designing something new, that's not going to be the first choice. Similarly, if someone is designing a new system that has the option to pick I3C, I believe people are going to switch to I3C.
That makes sense. Yeah, USB-A is useful. Just it goes in one way, whereas USB-C is reversible. Yeah, but it's a different protocol, right? So USB-C is probably more efficient.
Yeah. Again, same advantages like I2C and I3C.
Mm-hmm.
Right? USB-C offers faster data rates, is more useful for many more applications than what just USB-A was. And I think at Microchip, we understand that I3C is going to be crucial part of the future, and we will continue to participate in the adoption of I3C.
We're investing in development of the I3C protocol.
Yeah, we will focus on I3C in all the segments that it can be used.
Yeah, so I3C is not ours, right?
Yes, it's not ours.
It's from MIPI is a consortium.
Yep.
So what began your journey down this road to get to the I3C protocol?
Yes, we were not personally, Ashish and I were not involved since the beginning. MIPI started working on I3C protocol, 2014, 2015 timeframe.
Mm-hmm.
We were not involved at all. In fact, it was new for us even just a couple years ago. And the way we got into it was when an SSD vendor reached out to us and explained what their needs were. They needed to transition to a new solid state drive. They needed an I3C interface that could connect to the server rack. to the solid state drive controller with certain power requirements, speed requirements, and everything. And I3C was up and coming and was being adopted in the data center, and that's how we got involved, since we were now working on this new device. So it was a steep learning curve. We started by getting into the specs, the I3C specification that's available. There is a free version of the specification available, royalty free for everybody. And then there is a more like full complete specification available from MIPI for MIPI members.
Mhm.
And we started going through the specs. And then when the actual silicon arrived, we started testing whatever we have learned, programming the silicon, playing around with it like engineers. And definitely I would say that knowledge of I2C helped in understanding this new protocol since it was backward compatible. But overall, it was just learning, it took a while. It took a while to get used to it, and seeing it on silicon and understanding all those waveforms, how it works, what doesn't work, and some things that worked well, some things that we probably needed to fix, and it was a great journey.
Yeah, but it wasn't, we don't do that. Go find somebody else. We were adaptable. We were interested in finding ways to help the customer.
Yep. Yeah. So the SSD vendor that Max spoke about, we worked very closely with them on developing the actual silicon and helping them out with their application, having calls with them on a regular basis, getting feedback from them, and just feeding it back into our system and trying to make the product better.
I imagine it was a huge unlock for them.
Yes, definitely.
Great discussion, guys. Thank you so much for joining us.
Yeah, definitely.
A pleasure.
Ashish Mukhtal and Max Prasad are senior engineers of product marketing and applications, respectively, at Microchip Technology. They specialize in 8-bit microcontrollers and related technologies. They join us today from our global headquarters in Chandler, Arizona. Thank you for venturing beyond the microchip with us. Join us next time as we continue to explore empowering innovation to enhance the human experience.